All right. Good morning, good afternoon, good evening. Thanks for joining us again for another session of the Machine Learning Community Stand-Up. I heard your cries and I said, give people what they want. And yeah, so happy to be here, back with you guys. And with me are my co-hosts. I have Jake here and Bree. And with us today is Chi, who's going to be talking to us a little bit about AutoML, specifically FLAML. Chi, would you like to give a brief introduction of yourself?
Yeah, hi everyone. My name is Chi. I'm from Microsoft Research. I'm a researcher. I'm working with ML.NET team to improve their AutoML. Good to see you, everyone.
Awesome. Thanks. All right, let me just take a quick second here to switch over to our community links. Give me just 1 second here. I'm having a bit of trouble for some reason.
You're gone for one show and you forget how to use it all.
I know. I got a little bit rusty. Yeah, practice makes perfect. All right, cool. Let me switch here. All right, so that's not what I wanted to show. Actually, it is. Let me pause this for a second. So we often get questions about, are these shows recorded? Where can I find these shows? And the best place for you to get them is at this link here, the .net.microsoft.com/live/community standup. So paste that into the chat here. And essentially, you want to go to this here. And if you filter in this category drop down by machine learning, you're going to get the latest, all the latest shows and all of the past community stand-ups. So yeah, if you're looking for previous recordings or if you missed today's, you can definitely go back and watch that there. With that said, let me move on to the community links, and I'm going to grab that and paste into the chat here as well. And first off, we have here Logic Geek with a video that talks about discovering machine learning using ML.NET. And essentially what Logic Geek goes through here is basically how you can use something like Model Builder to train, I believe it's an image classification model for, if I'm not mistaken, let me see if I can find it here. It's using it for chest X-rays. All right, so I think the data set comes from Kaggle. And yeah, so Logic Geek here just goes through how you can use Model Builder and ML.NET to build these types of models. We also have another video here from the Microsoft Reactor. And in this case, we have Arfa here talking about how you can use ML.NET to introduce or add machine learning to your .NET application. So make sure to check that out. Also, the global AI community recently had an event. And for that, Marco Zamana here, who was actually also part of the virtual ML.NET conference almost a month ago now, essentially just talks a little bit about how you can use ML.NET, for the different scenarios. So give that a look. If you're looking to get started with ML.NET, there's actually two courses. There's this one here, which was recently updated on Udemy. I think that's how you say it. And it's just machine learning for beginners with ML.NET. It was recently updated in May, and it takes you through the various parts of how you can use ML.NET for different tasks. Also, we have this course on LinkedIn Learning from none other than, his name doesn't show up here, but this is from John Wood. So if you are familiar with John Wood from his many YouTube videos, he now has an official LinkedIn Learning course. So make sure to give that a try and give some feedback. And you also get a really nice certificate if you go through this course and complete it. I am now ML.NET certified, so now I can put that on my resume. There's this other cool application that I ran into this morning that I hadn't seen, but it's called Knott's Falcon Cam. And what Knott's Falcon Cam essentially does is, or at least my understanding, so Knott's Falcon Cam, if you are watching the stream, correct us if we're wrong, or if you watch it at a later time, feel free to reach out because it's an interesting use case. But essentially, my understanding of this is that there are some live stream cameras set up. Let me just go to that page here real quick. I don't know if it's going to be too slow here. But essentially, there's this cam that's set up, and it's just looking at this one spot. And then it uses ML.NET apparently to process the live stream. And whenever there is a Falcon that shows up, such as in this case here, it uses this ML.NET model to detect, hey, there's a falcon in the frame in the image. Let me post a tweet that I saw this falcon, and it adds additional information such as weather info and other comments here. So yeah, that's make sure to check it out. And again, if Nod's Falcon Cam is you're watching or you'd like to share this, we'd love to chat with you. And then last but not least, we have here a blog post that Bree, would you like to talk a little bit more about what recently happened in June?
I would love to. So this one was a pretty big one for both ML.NET and our tooling. So for ML.NET, we are finally releasing ARM support, which is awesome. So you can now perform training and inferencing with ML.NET on ARM64 and Apple M1 devices. Of course, that's in addition to already being able to use it on Windows, Linux, and Mac. We have a video here of Louise training on, I think last time I was told it was Manjaro, right? ARM. So there's a little video just showing the OS information and then actually training the model and using it successfully. There's a few limitations which you can read about, and also, just as a heads up, this is technically the release hasn't come out yet. I think it's going to be 1.5.6. So you do have to build it from the source, but you are totally welcome to try it out that way. And then in the next few weeks, we'll get the NuGet package updated. So that's that. Also, just a little bit more information about ML.NET on Blazor WebAssembly. With .NET 6, you can perform some training and inference there, but there are the same limitations as with ARM. And if you have issues with some of these limitations, or there's still a scenario that we're not covering in terms of training or inferencing environments, please let us know in our GitHub repo, and we can take a look at that. And then model builder updates. So this is the one that we've been talking about for quite a while, that we had our preview for. So this includes that config-based training with those code behind files, which is what's shown in the screenshot there. Also, some more advanced data options, a redesigned consume step. There's also these project templates at the end of the consume step, so you can generate projects that will consume your model. So previously, we would auto generate 2 new projects in your solution, one for training, retraining, and one for consumption. And there's like a sample console application. Well, now you can choose, hey, I want to add a new project, which is a console app, or I want to add a new project, which is a web API. And then, for instance, if you do the web API, you can just right-click deploy if that's how you wanted to do it, or right-click publish. And we are open to adding more project types as well, such as Azure Functions. Again, leave your feedback so we know what kind of templates you want to see there. So I won't get too much into this, but we do have a new and improved AutoML, which Chi later on will be talking about. We've been partnering with Microsoft research teams NNI and FLAML to just improve our AutoML experience behind the scenes. So check out this section if you want to see kind of why we're doing this, some of the benchmark testing that we have between the old AutoML and the new AutoML, and you can take a look at that. You can see there's been a huge improvement in the number of models that are trained in the given amount of time, and so on. So that's a lot of what the focus has been on, is being able to train more models in the given amount of time, making sure that there's in the amount of training time that it doesn't time out without training any models. And we're also looking to improve the overall model performance as well. So you can check that out. Then just some bug fixes that came about from the preview. So thank you to everyone who tried out the preview and left your feedback. We were able to fix a lot of bugs that way. And there's still a few more suggestions, feature suggestions that we're working on, which I guess I can talk about what's next in Model Builder. So this most recent release, you can only use absolute paths for training data sets, which means it's kind of hard to share over Git or with source control, but we're going to update that in one of the next releases so that it's a lot easier to collaborate with source control on these MB config files. I've also been working on performance improvements, especially around larger data sets, loading larger data sets in Model Builder, continuing to work on some AutoML improvements, and then we just started working on this kind of continued training feature, which right now, you start training, you have to wait till the end of training. And then once it's done training, those are the models that you have. Continue training will allow you to, if you don't have the model that you want at the end of training. It will save that training progress, and you can continue the training on from there without having to restart the status. And then tighter integration with Azure ML, including through Azure ML dataset support through Model Builder. So those are some of the things that we're working on coming up with Model Builder. There's also a bit of information about the ML.NET survey that we did earlier this year. In another stand-up that we did, I went over the results. So I believe I went over all these results, but now it's in this blog post as well. And I don't think in that one we talked about kind of the next steps that we would take based on the feedback we got. So here are some of those things based on, the top pain points that we saw. What are some of the action items we're going to take to alleviate some of those challenges? So for instance, for small ML.NET community came up a lot. So, we're going to continue with our community efforts, such as these stand-ups. We have an ML.NET Discord channel, which maybe Louise can find the link to and post that in the chat. We did have a Slack channel, but there's too many people on it now. Apparently there's a limit for the free version, which is being maintained by community members. So I think it's being moved over to Discord now. And yes, some other things is making sure that we, as well as other community members, are active on Stack Overflow, GitHub, encouraging community contributions and such. For the challenge of insufficient deep learning support, we're currently defining our plan for deep learning in ML.NET. Some of you watching, we may have even met with you to talk about your requirements. So that plan we'll start talking about a bit more in the coming weeks, but that will include things like torch support and adding features for building neural networks from scratch. And then lack of and quality of docs and samples came up quite a bit as well in the survey. So we've got some more dedicated resources on docs, including Louise, who's an awesome content developer. So we'll be continuing to update that, and as well as adding more complicated end-to-end samples and tutorials. And you can take a look at the other ones here as well, because I don't want to take up too much of the time, which Chi will be talking about. And then I think, Louise, if you scroll down, so then the rest is just some of the resources to get started there. Those are some of the updates, which are, let us know what you think about any of these. It links in the blog post to the GitHub repos. So feel free to leave your feedback or any questions or comments there.
Awesome. Thanks, Bree. So with that, let's turn over to Chi so he can show us all the amazing stuff that's in FLAML. So let me switch over here. All right, the floor is yours, Chi. I think you're on mute, but take it away.
Great, thank you very much. Thank you so much for the introduction. Good morning, everyone. I've done introduction, but in case you missed it, my name is Chu. I'm a researcher from Microsoft. I'm working with the ML.NET team to improve the model builder. In this talk, I will introduce the fast and lightweight AutoML technology, FLAML, from Microsoft Research. Okay. More and more teams start building millions of machine learning embedded applications. It adds up to a large cost to manually tune the hyperparameters and choose the right machine learning algorithm for every task and every dataset. AutoML tools automate this process and reduce the human effort, but they often consume large computational resources, especially for large-scale training data. In a typical AutoML pipeline, hyperparameter optimization is usually the core component. HPO is mostly treated as an expensive black box optimization problem with high resource consumption. For example, when using gradient boosted trees, we need to tune the number of estimators, the number of leaves, learning rate, etc. It may take hundreds to even thousands of trials before the tuning stops, and each trial can take tens of minutes on large data sets. And it can be much longer for deep neural networks. The end-to-end tuning for large neural networks can easily span to multiple days or weeks. Our project is targeted at HPO and more generally, AutoML solutions with much lower computational cost than existing solutions. We design our solution to be fast, economical, and scalable. In the same time, we make it easy to use and customize for different use cases. We have built a few artifacts for tuning model quality and inference latency, respectively. I'll focus on multi-quality tuning in this talk. We begin with inventing a simple and provable local search algorithm called flow square. With that, we develop a cost-frugal optimization method, CFO. It is published in AAAI conference this year. We further extend it to combine with global search and make a framework called blend search. Finally, we build a fast and lightweight Python library, FLAML. FLAML is also the first AutoML library that supports online machine learning models. FLAML can be used in several ways, depending on how much customization you need. With 3 lines of code, you can start using this economical and fast AutoML engine as a scikit-learn style estimator. You can restrict the learners and use FLAML as a fast hyperparameter tuning tool for XGBoost like GBM, Rainforest, etc., or a custom learner. You can also run generic hyperparameter tuning for fully customized function and search space. Our library has provided example notebooks for each use case. Let's quickly check out some demo.
Hello everyone, welcome to the tutorial on FLAML. FLAML is a Python library designed to automatically produce accurate machine learning models with low computation cost. It is fast and economical. The simple and lightweight design of FLAML makes it easy to use and extend. You can choose your desired customization depending on your needs. In this tutorial, I will show you how to use FLAML with different levels of customization by going through several notebooks. You first need to install FLAML and get your datasets ready. Currently, FLAML supports AutoML on classification or regression datasets. For example, in this notebook, we load a classification dataset from OpenML. If you are a domain expert without much knowledge about machine learning, you can use FLAML with the minimum customization. You can start using it as a scikit-learn style learner with just 7 lines of code in the following way. You first build an AutoML instance from FLAML and specify the most basic information about this task. Such as the time budget for this AutoML task, the metric to do AutoML, the type of the task, and etc. Then you can call this fit function to do AutoML, which will finish within your specified time budget. After fitting is finished, you can easily retrieve the outcome of the AutoML instance. For example, you can look at the best learner font, the best configuration for the best learner, the best accuracy on the validation dataset, and also how long does it take to train the model with the best configuration. In fact, if you can also directly output the best model or dump the AutoML instance for future usage. Here, let's directly use the best model to do the prediction on the test dataset, which can be achieved by calling this predict function. And then we'll look at the prediction performance. If you also care about the anytime performance of the AutoML process, you can check out the logs, where you can see the search trajectory. Here, we are plotting the anytime performance of FLAML in terms of validation accuracy, which looks quite promising. In this example, you may notice that we didn't actually specify any learner or search space. Under this minimum customization, FLAML is actually searching over a set of default learners, which each with their corresponding search space already coded in FLAML. If you are a machine learning engineer or innovator and want more customization in your AutoML or hyperparameter optimization process, you can also easily do that in FLAML. For example, if you want to include one or several of the particular learners in FLAML, you can achieve it by configuring the estimator list argument in the fit function. For example, in this notebook, I only want FLAML to search over hyperparameter configurations of the learner like GBM. I can do that by including only this particular learner in the estimator list. And there I set the time budget as 2 minutes. After 2 minutes, you can check out the results by looking at anytime R2 score on the validation dataset, or the R2 score on the test dataset. Since we have the result, let's by the way do a quick comparison between FLAML and the default LightBM without any tuning. We can see that FLAML can indeed give a much better score than the default LightBM. Then let's also briefly compare FLAML with another hyperparameter optimization library, Optuna. In this example, FLAML's score is also much better than Optuna. And note that Optuna actually used 4 minutes to obtain this result. And if you remember, FLAML only used 2 minutes, which is half of the resource. If you want to include a particular learner that is not among the default ones in FLAML, you can also easily add them. Suppose you want to include this regularized greedy forest learner, which is not currently included in FLAML. Here is what you need to do to add it. First, you need to have an implementation of the customized new learner. Here we are obtaining it from the scikit-learn library. Then you need to specify the search space, which includes the list of hyperparameter names and types and the ranges of the hyperparameter configuration. Optionally, you can also provide initial values for the configurations. In addition, FLAML encourages users to provide a low-cost initial value for those cost-related hyperparameters in order to take full advantage of FLAML's unique search strategies designed for cost-related hyperparameters. Here, let me clarify a little bit about the cost-related hyperparameters. A cost-related hyperparameter means a hyperparameter whose configuration value have a direct impact on the evaluation cost of the corresponding model. In this example, the max number of leaves, number of iterations, and tree search are all such types of hyperparameters. And here we provide a low-cost init value for each of them, which is just an arbitrarily small value in the search space. After coding up this RGF learner, you can now add it into FLAML by calling this addLearner function. Then you can run AutoML by tuning hyperparameters of RGF as well as the default learners. In addition to adding customized learners, you can also customize the evaluation metrics and other options or many other arguments in the fit function depending on your needs. Finally, FLAML also allows advanced users to do hyperparameter optimization with arbitrary training and evaluation code in FLAML.tune. FLAML.tune is a module for economical hyperparameter tuning. It can be used standalone or together with ReTune or NI. In this README, we include an example of sequential tuning with some arbitrary evaluation code. Here I include the configuration evaluation code in this eval config function, in which I report the result of my interest as the metric. The hyperparameter optimization is done by calling the tune.run function, where I provided the evaluation function, the search space, the low-cost partial config, which is the low-cost initial config value for the cost-related hyperparameters, as explained before, and the time budget in seconds. After it finishes, you can retrieve results of your interest from the returned analysis object. For example, from there you can look at the best trials result and the best configuration. If you are familiar with ReTune, you can also use ReTune's API in almost exactly the same way. The only thing you need to do to use our method is to specify the search algorithms accordingly. The two uniquely economical hyperparameter optimization proposed in our library are CFO and blend search. In fact, these two hyperparameter optimization algorithms are already integrated into ReTune recently. You can also check them out there with the corresponding examples. You can find another example of using this tune.run in this notebook. In this notebook, we fine-tune a transformer model from Hugging Face transformer library. Similar to what is previously introduced, you can define a training function which accepts a hyperparameter configuration and reports the metric to optimize. Then you provide the search space of the hyperparameter configuration and call flaml.tune.run to do the hyperparameter optimization within your time budget. You can also control parallelization by specifying the resource per trial argument. And again, you can retrieve results of your interest from the returned object. This is the end of this brief tutorial. Thank you for your interest and attention. For more details, please feel free to check out our notebooks, test cases, and the documentation in the FLAML library. We welcome your feedback and contribution. Thank you. Hello, everyone.
Okay, let's get back to the research behind FLAML. The main insight of FLAML is to optimize for low computational cost in finding accurate models. The trial cost, meaning the CPU cost of training and assessing the model error, is explicitly factored in the optimization problem. That's different from existing AutoML solutions. The main idea is to design an efficient search order to control the overall trial cost before finding low error models. Recognize that the cost of one trial is related to the following variables: the learner, a subset of the hyperparameters for the chosen learner, the size of the training data, and the resampling strategy. For example, it's much more expensive to perform a 10-fold cross-validation trial for a scikit-learn random forest with 1,000 trees and 1,000 leaves on 1 million training examples than the holdout trial for XGBoost with 10 trees and 10 leaves on 1,000 training examples. Intuitively, the order of trying these choices has a huge impact on the search cost. We need to avoid unnecessary expensive trials to save the total cost, but we also need to perform such expensive trials early enough if they are indeed required. We analyze the relation of these factors. In this figure, we'll analyze the relation of these factors. In this figure, the 4 factors determined by the search algorithm in each trial are marked with dotted circles. The cost and the validation error of each trial are observed after the trial is finished. The test error is not observable during AutoML. It's approximated by the validation error. We want to minimize test error and at the same time minimize the total cost of all the trials. We observe several relations among the variables. They are not first noticed by us, but they are rarely leveraged by existing AutoML systems. Here I'm showing one example of the observations. Many learners have a subset of hyperparameters related to model complexity or regularization. For example, the number of trees and the depth of each tree in tree-based learners. For a fixed sample size, the test error doesn't necessarily reach its minimum at maximal complexity. Generally speaking, smaller sample size requires lower complexity and more regularization to avoid overfitting. Based on these observations, we propose a few properties for efficient AutoML system. We can use small sample size to train and compare low complexity configurations, but we need large sample size for comparing high complexity configurations. We prefer cross-validation over holdout for small sample size or large cost budget. Given any search sequence prefix, each learner should have a chance to be searched again, unless all the valid hyperparameter values have been searched using the full training data size in the prefix. We desire the total cost of any search sequence prefix to be approximately optimal with a bounded ratio over the optimal cost for the lowest error rate achieved. Although these properties are idealistic properties and they are not necessarily complete, they provide meaningful guidance in designing a low-cost AutoML system. Based on these design guidelines, we propose a novel adaptive system to choose a search order optimized for both cost and error. The AutoML layer includes a learner proposer, a hyperparameter and sample size proposer, a resampling strategy proposer, and a controller. The order of the control flow is indexed on the arrows. It iteratively decides the learner, hyperparameter, and sample size at each search iteration on the fly. Changing one strategy inside each component doesn't affect the strategy of the others. This design allows easy upgrade by incorporation of normal search schemes to replace each component. At the conceptual level, our system differs from previous work in how we decouple the search variables and search strategies, as the table shows. For example, we couple the decision of hyperparameter and sample size before the model complexity needs to fit the data complexity. We decouple learner and hyperparameters to respect domain dependency. For the learner choice, we prioritize them dynamically using a notion of estimated cost for improvement for each choice. We use a similar notion to decide when to increase sample size. Basically, we prioritize learners with lower ECI. For hyperparameter optimization, we develop our own cost-effective optimization method, which is published in AAAI this year. It gradually converges from cheap trials and inaccurate models to expensive trials and accurate models. And the total cost is bounded by a constant factor of the cost of the optimal configuration. We modified it to make it propose both hyperparameter configuration and sample size. We choose between changing hyperparameters and increasing sample size by favoring the choice with smaller ECI. ECI considers model error and trial cost holistically and adapts the priority based on the search trajectory corresponding to each choice. For example, the figure on the left plots the best error per learner versus AutoML time, and visualizes the ECI of two learners, LightGBM and XGBoost, when the current time point is 35 seconds. The calculation of ECI for a learner is based on the assumption that it takes higher cost to find an improvement in the later stage of search. It's calculated depending on whether the learner currently has the lowest error among all the learners. The figure on the right visualizes the search trajectory of each learner. The ECI-based prioritization favors cheap learners in the beginning, but penalizes them later if the error improvement is slow. To explain more about how the ECI is calculated, let's look at the figure on the left. The LightGBM currently has the best error, so the ECI for LightGBM represents the cost it takes to find a better configuration for LightGBM itself. We compare the time between now and the last improvement here, and the time between the last two improvements, and use the longer of them as ECI. XGBoost currently has higher error than LightGBM here. So the ECI for XGBoost corresponds to the cost needed for tuning XGBoost to bypass LightGBM performance. To calculate that, we project its future performance based on the recent speed of improvement. Suppose we choose XGBoost for the next trial, it finished at 38 seconds and does not find a better model. In this case, the ECI of XGBoost will be increased as shown in the horizontal orange arrow, and the priority of XGBoost will be decreased. Our search strategies are designed toward both strong final performance and anytime performance for ad hoc datasets. Our system tends to propose cheap configurations at the beginning stage of the search, but quickly moves to configurations with high model complexity and large sample size when needed in the later stage of the search. These designs make FLAML navigate large search space efficiently for both small and large datasets, without relying on expensive preparation such as meta-learning. In fact, our system has almost no computational overhead beyond the trial cost of each configuration. We don't have time to explain every detail of the system, but this slide gives an example of a search sequence so we can get an idea how the algorithm works. Every iteration will choose one learner, one configuration of the learner, and the sample size. Here we have 3 learners: XGBoost, LightGBM, and Random Forest. In general, the error decreases as more time is spent for each learner. For each learner, the search always starts with the smallest model, and the training can finish in a very short time. For example, LightGBM starts with 4 trees and 4 leaves, and the training takes 30 milliseconds. The model complexity quickly increases in the geometric step, so we see that within 4 seconds, the complexity for LightGBM already grows from 4 trees and 4 leaves to 600 trees and 20 plus leaves. In general, more iterations will be spent on the most promising learner. In this case, even though initially Random Forest has the lowest loss, LightGBM's loss decreases faster, and more iterations are spent on LightGBM. By increasing model complexity doesn't improve the loss for learner. We increase the sample size, for example, for Random Forest at iteration 26. I hope you get a rough idea of why FLAML is efficient. Now let's look at experimental results to see what difference this optimized search order makes. We use 53 classification and regression benchmark datasets. They have a good diversity of scale, type, and difficulty. All the datasets are publicly available on OpenML. We compare FLAML with 4 trial-based AutoML libraries, plus a hyperparameter optimization library designed for budget-constrained scenarios. AutoSKLearn, H2O AutoML, and TPOT are top-ranked open-source libraries in the AutoML benchmark. Cloud AutoML is a commercial cloud-based AutoML service from one major cloud provider. HB Banster is an implementation of Bob, which integrates Bayesian optimization with Hyperband. It uses the same search space and resampling strategy as FLAML. The referred AutoML classification benchmark uses ROC, AUC, and negative log loss as the scores to evaluate the performance on binary classification tasks and multi-class classification tasks, respectively. It calibrates the original scores using a constant class prior predictor and a tuned random forest. So the constant class prior predictor as 0 and tuned random forest as 1. The higher the better. The tuned random forest is a strong baseline taking a long time to finish, and achieving a score above 1 is not easy. For regression tasks, we use the R-square score before calibration. These radar charts plot the normalized scores per dataset on classification AutoML benchmark given different time budgets. On regression tasks, FLAML has a similar superior performance. This slide summarizes the evaluation result. Look at the box plot charts on top. It shows the distribution of score difference between FLAML and each competitor at different time budgets. With varying time budget from 1 minute to 1 hour, FLAML outperforms top-ranked open-source AutoML libraries, as well as a commercial AutoML service in most of the tasks given the same budget. FLAML has a significant advantage over all the others. Now look at the figure on bottom. Each box plot shows the distribution of score difference between FLAML and each competitor when FLAML uses a smaller time budget. For example, the last plot, 60 seconds versus 3600 seconds means FLAML's time budget is 1 minute and the concerned competitor's time budget is 1 hour. FLAML's performance in 1 minute is already better than or equal to most competitors in 1 hour on more than half of the tasks. FLAML has both internal and external users. The top 2 reasons they chose FLAML are: number 1, it improves their productivity by reducing the time required to iterate on the model building and tuning process by orders of magnitude. Number 2, they like the ability to customize the tuning objective, as they each have specific goals or constraints. They found FLAML provides simple ways to address their requirements. We have made quite a few other extensions. Our hyperparameter tuning method can be used with distributed frameworks like Retune or NNI. We recently added support for online learning and transformer-based language models. Wabbit is an example of online learning library from Microsoft. The idea of a canonical hyperparameter optimization is applicable in many scenarios. What we have explored so far is just a small corner of it. Our North Star is to remove the manual hassle of hyperparameter optimization for data scientists and engineers. Please check out our library on GitHub and share your feedback. So that's the end of the presentation of this research technique. So let's take some questions from the audience.
Awesome. Yeah, we have a few questions here.
Yeah.
Yeah, let me add Jake back to the stream. Lost you for a bit there. Okay, so yeah, thanks for sharing that. Actually, that very last slide on Ray, I wasn't really aware that it worked with Ray, but that's really cool to see. I know that Ray is used even in like reinforcement learning scenarios quite often. But
yes,
anyway,
yes, that's right.
Let's get to Sarah's question here. Does FLAML have a NuGet package that you can use inside of a Blazor application?
So so here the FLAML.
I'm not sure if I'm frozen or not.
Nope, you're live. Yeah. Sorry. Go ahead. Go ahead, Chi.
I was just going to touch on it and say, like, we want to bring FLAML to a NuGet package, sort of indirectly. So right now, in the ML.NET tooling, like Model Builder, and the soon-to-released version of the CLI, we leverage NNI and FLAML there. We've kind of been iterating on the code side first, and we're eventually going to try to migrate that into the framework, so into ML.NET. So although it's not available today, you asking for it here actually helps us make the case that it needs to happen. And if you can comment on the machine learning repo or the tooling repo, leave some comments there. That'll help us sort of accelerate that over some of our other tasks if it's really important to you to have a code-first approach to AutoML instead of just using our tooling to do that AutoML for you.
Speaking of tooling, we have, I lost it there for a second. So Sharafuddin asks, are there any tools which can do these things in this step? So I think, Sharafuddin, to clarify, I think this question was made while playing the video that was going over the different steps and things that you would use FLAML for. So, with that context, are there any tools that you can use FLAML inside of?
Yeah, so I guess this question is for the Python library. So for the Python libraries, we don't have a graphical interface. It's just a pure code-based approach. So we can install the library, run just the fit, either the fit API or use the tune down run API, just a single function call you can make. But for the ML.NET version, the model builder, there's a very nice graphical interface and the UI to go through. So if you're not familiar, probably Jake can give some brief introduction about the tooling there. So in the .NET, there's indeed a very good tool to use.
Awesome. Yeah, there's we'll wait. We lost Jake for a bit here, but we'll wait to ask a question because I think there was another one from Sharafuddin as well as sort of scenarios that are covered by FLAML. But we'll just wait for that and instead move on to another one here. Oh, there we go. Can you hear us, Jake? All right, we'll move on in the meantime. Oh, you can hear us? Okay, awesome. So there was a question here from Sharafuddin as well, which asked, is there any FLAML model for point of sales application which can integrate with Blazor? So I think maybe this question we can answer from the standpoint of like what FLAML scenarios are supported inside of Model Builder.
Yeah.
That question's for you, Jake.
Sure. So all of our local training scenarios are now powered by FLAML. Actually, one correction. Right now, we don't have image classification supported by FLAML. It's still using our image classification API. But all the other scenarios are going to be trained using our integration of FLAML and NNI pick the best model.
And I think that helps answer this next one, which is, can I run FLAML locally? But maybe, Chi, you can talk about if there's any prereqs for that.
Yeah, so to run the Python library locally, it's really very simple. You just do a pip install FLAML. It will automatically install the dependency. The dependencies are quite small. It's just NumPy, LightGBM, XGBoost, some very common libraries that you will use in data science. And there are a bunch of actual requirements if you want to use the extended functionality. For example, if you want to run the hyperparameter tuning method FLAML in a distributed framework, you might also want to add install either retune or NNI. So we also provide these extra options that you can use, and there are also options for online learning and natural language processing tasks specifically. Those are actual add-ons. But in general, FLAML is very lightweight, and the dependency is kind of, we try to make it minimal so that you don't need a lot of extra requirements. So for I'm not sure if there's a corresponding question for the .NET version that Jake, you can comment on.
Sure. Yeah. For the .NET side, Bree kind of showed off the blog post earlier. If you download the latest version of Model Builder, it'll have everything you need. So the prereqs for that are, I think the blog post usually links to the install and install instructions, but you just need to install Visual Studio and then Model Builder on top of that, and then you're good to go.
So speaking of Ray, which I brought up earlier, Jose asks, what's the relation between Ray, Anyscale, and FLAML?
That's a very good question. So Ray is a very generic distributed framework to run your programs in a distributed environment. So it can do a lot of different things, including reinforcement learning, training large-scale models in distributed framework, and also can do hyperparameter tuning via this retune component. So the hyperparameter optimization method offered from FLAML can also be used in the retune framework. If you want to do distributed tuning, there's a nice interface from retune that you can plug in all different hyperparameter methods, and FLAML's method is already merged there, so you can find out that. So actually, it's not released in the current retune version, but it will be released in the next version, like 1.5.0, and we have merged that request. And you can use the same technique either using FLAML CPI and retune CPI. They're compatible. And also our hyperparameter tuning method, for example, if you want to define the search space and so on, you also just need to use one single API to define all that. So there's no difference in retune and FLAML. So really, FLAML is mainly focused on the core search algorithm. So it offers alternative search algorithm that is cost efficient. That's the main novelty and innovation of FLAML. And retune can do all the kind of distributed processing and checkpointing, failure recovery, all this kind of job patching and scheduling for you in the distributed form, because that's the relation. So there is a backend for distributed computing. And we're actually working together with the Ray team on the blog post, and so you will see more how these two are integrated.
Awesome. Expanding upon on these extensions, right? I think I saw one of the other ones that's super exciting, and I think is also in line with what Bree mentioned in the blog post in terms of what the team is working on, next steps, and so forth. But that integration with Hugging Face and transformer-based models, could you talk a little bit more about that?
Yeah, so we recently added experimental support for automating the tuning of transformer-based models especially from Hugging Face. So for example, you can tune BERT, some larger variations of BERT to do fine-tuning on different downstream tasks. Because for these pre-trained models, so every downstream task like classification, question answering, you need to use your own training data set and fine-tune these large-scale models specifically. And that's, although it's less expensive than pre-training, but you remember that pre-training, you only need to do it once for one model, and you can afford some expensive training because it can be used multiple times after training, and you will not repeatedly train again and again. But for fine-tuning, more likely you will need to repeat this process for many different tasks, and also even when your training data changes, you want to do that again. So this is a repeat process. So although one single time of fine-tuning is less expensive than pre-training, the combined cost of doing the fine-tuning is still quite large. So we provide this new API called Auto Transformers. So that has two advantages. So one is to fine-tune existing model from Hugging Face. Previously, you'll need to write lots of customized code, like load the data, load the model, add some customized layers to the model, and then set hyperparameters and train the job and evaluate the models and so on. So you need to write at least like 500 lines of code if you just look at some example from Hugging Face library. And with this new API, you only need, again, only a few lines, and it can automate many steps for you. And another advantage is you can leverage the hyperparameterization methods from FLAML to do the hyperparameter tuning for the fine tuning as well. So it's we actually recently had some empirical study about also how to troubleshooting this hyperparameter tuning and so on. But we are not finished yet, so we are still working on improving that functionality, and you will see even more better fine-tuning solution from us in future.
Very cool. I really like that sort of pre-processing. I think a similar sort of challenge occurs with Onyx-based models, right? Where there's this boilerplate code that you always have to do for pre-processing images and for post-processing, the outputs from the model. And this is code that, people often write, but for state-of-the-art models, let's say, for example, BERT or, any other vision model, it's code that you already know how you need to pre-process and post-process that. So automating that, and I think in the Hugging Face scenario, right? Does that also cover tokenizers as well? Like the tokenization strategy, or is that something that users will have to do separately?
It's covered. So in Auto Transformers API, inside it will also select the tokenizer, apply the tokenizers automatically. So that's. But one caveat is right now it's for the glue tasks. So glue is a common benchmark used for the natural language benchmarking. So it includes a diverse set of tasks already, but there are also other tasks beyond that. So we also need, in future, that we need to extend the support for those different tasks, like super glue and generation, natural language generation. Yeah. But usually glue is the first benchmark you go to when you do your finding.
Nice. We have a question here, and maybe could provide a little bit more clarity on this. Mm-hmm. Sharafuddin asks, if we use FLAML, then we don't need to use Onyx to integrate with Blazor. And yeah, maybe let's see. Chica, you could provide a bit of clarity around, what components does FLAML do? Because my understanding is Onyx would be only for deploying the model, right, and sharing it once you have a model, whereas FLAML is for actually training the model, not really for consumption. So, but maybe you can provide a clarity there.
You're right. So FLAML doesn't do anything related to deploying the model. So the API for FLAML is you run the fit of the on your training data, and it will produce a model as output. This model, it's just like any other scikit-learn model or LGBN model you use usually. You can expect the hyperparameters and so on, but when you deploy the model, you still need to take the models to your deployment environment and apply it. So that part we have not done any change to the deployment steps in FLAML.
From the integration standpoint, though, like with Model Builder, the output from the training is that you'll also get training code and consumption code. Mm-hmm. And depending on what learners it's using, you may or may not be able to use the MLNet model and code directly instead of trying to convert it to Onyx or anything like that. So that may have just made the answer more complicated. I think you'll have the option, I guess, for your deployment to export to Onyx, but as part of our work for lighting up ARM support and a lot of our cross-plat, we're trying to make all of our models and learners more compatible with things even like Blazor WebAssembly. So hopefully you could use ML.NET directly and not have to go to Onyx, but Onyx is an option.
Very cool. So if I remember correctly, one of the things that you mentioned in terms of the strategy and how FLAML selects models, I think you mentioned that it favors cheap trainers or cheap learners, when it's a short amount of time, and then it sort of penalizes them later on. Are there any sort of, I guess, learners or algorithm types that you find recurring that that are often picked more often than others in FLAML training scenarios?
Yes, definitely. The most common winners in terms of learner type in our benchmark dataset for classification and regression are LGBN. LGBN probably number one in terms of frequencies it wins, and follow it's I think it's CatBoost, XGBoost, and Random Forest, sometimes XRGs. The linear learners usually, I think in about 50 plus datasets, it probably only performs well in 1 or 2 cases, so it's rarely a winner. But that's empirical observation. I'm sure, like for different tasks, you can't predetermine for each like specific task. You can't pre-decide which learner is best. You still need to try the different ones. And some of the libraries, for example, they are good at, for example, handling raw categorical features, right? So that's one example. Like it depends on the specific task and the data set, which learner is best.
Right. That makes sense. Mm-hmm. Let's see here. If you have, because I see we're running a bit short on time here, we got about 2 minutes left. So if you have any last minute questions, make sure to go ahead and paste them into the chat regarding FLAML and AutoML. With that, maybe you mentioned it, but what are some things that you feel? Well, folks are typing the questions there. What are some things that you feel FLAML wants to focus on next, and what are sort of your big, sort of goals, going forward for FLAML?
Yeah, so that's a very good question. We are so there are several things currently we support them, but we further want to improve. So one is the natural language scenario I already talked about. Another is the online learning scenario. So this is really very new. So no existing AutoML library can do the height tuning for like online learning. So we have a recent research paper published in SML and to handle that. But it's just a beginning, and we need to make it more mature to support the real use case in production. So these two are some very active working areas, and we also want to add better support for constraint optimization, including, for example, responsible AI and fairness constraints. And one more thing is I'm also interested in applying the method in FLAML to the neural architecture search. So that's a very active area in AutoML. Because recently there are some finding that the local search method performs quite well in the NAS benchmarks if you give them enough time. But that one was based on very naive local search method, and we wonder that maybe with our more advanced search method, we can make more progress there. So yeah, these are some things in my mind.
Awesome. Yeah, that sounds really exciting. It seems like some of our audience members here are definitely excited as well to see, what's next for FLAML, and, especially within the .NET community, how some of those, those new features and capabilities sort of, flow over into the .NET space through ML.NET. So we are at time. Again, thank you, Chief, for joining us and showing us FLAML. It's really exciting, the work that you folks are doing. It's really exciting, and yeah, can't wait to hear what's next. So with that, thanks for joining, and we'll see you next time. Take care. Bye.
Thank you very much.